Hi everyone, welcome back to drawing. Instead of in class, we're here at Fourth Culture Studios. That's my studio and I call it Fourth Culture because there's culture, counterculture, the reactionaries, and then there's us, Fourth Culture Studios. So today we're going to cover linear perspective. We're going to start with 1-point perspective, then we're going to go to 2-point perspective, 3-point, incline plane, stairs, including spiral stairs, ellipses, using the 8-point tangent system, and we'll do cube multiplication or diminution in space. To get started, we have a few terms to cover. One of our first terms is the picture plane. The picture plane is an imaginary plane in between the artist and the subject. That plane just is the surface of your drawing. An example of that would be if we have that surface of the drawing, and then we have the artist and the subject. Picture plane. Our next term is horizon line. We'll abbreviate that with HL. The horizon line is a line where sky meets ocean. That horizon line is also called the eye line, and it's called the eye line because that horizon line is at the same height as the viewer's eye. If you climb up on a ladder, then the horizon line goes up. If you sit down, then your horizon line goes down. It always is the same as your eye line. If I take that picture plane, and here we have an imaginary picture plane right here. If I take that picture plane and I move that up, my horizon line stays at my eye level. So now my horizon line has dropped below my picture plane. If I go down, then the horizon line goes up above the picture plane. So the horizon line, it doesn't always have to be right on your paper, but it does reveal your eye height, your eye line. Okay, number 3 is ground plane. The ground plane is just the plane that all of your objects are sitting on. So if I'm drawing a landscape, then it's just the ground. If I'm drawing an interior, then it's the floor. Associated with the ground plane is ground line. The ground line is the point at which the ground plane intersects with the picture plane. Our next term is scale. In a drawing, you can do a drawing to scale, like think about architectural renderings. And the scale would be, for example, 1 inch equals how much in real life? Maybe it's 12 inches. So that would be 1 inch equals 12 inches. It's at that ground line where the scale holds. So if we have a scale of 1 inch to 1 foot, then at the ground line, that 1 inch would equal 1 foot in real life. So if we were to draw a cube there, and it was a 12-inch cube, then that would just be 1 inch wide 1 inch tall to give us a 12-inch cube. We call that the mother cube. All right, the next term is cone of vision. The cone of vision intersects the picture plane at a certain point. Now, why this is important for us in linear perspective is that if I draw outside of my cone of vision, then I'm going to get a pronounced distortion. So we want to think about things like a fisheye view. If I want things to be not distorted, then I need to keep them within the cone of vision. Let's just continue that out. Okay. So we've gone over picture plane, horizon line, eye line, ground plane, ground line, we've touched a little bit on scale, we've touched on cone of vision. Let's go back to that mother cube. If that is really a cube, then we're going to have that 3 dimensions. And what linear perspective is capturing is that sense of convergence, and the way that that convergence seems to, if I was to use line extension and just draw those lines all the way out, it seems that they vanish on the horizon line. So now we can talk about the definition of one-point perspective. I've got my picture plane, and then I've got a cube or a cube-like form that is parallel the picture plane. It has at least one side that is parallel the picture plane. And then its diminishing edges seem to vanish at one point on the horizon line. So one-point perspective is also called parallel perspective. Let's jump to the drawing. All right, so let's get started. A few implements that you're going to want to have. Pencil, a ruler. I actually prefer a stick, unless of course we're getting into scale. To set our cone of vision, we'll need a ruler. So let's start with our horizon line. Now, as we discussed, the horizon line is somewhere on the picture plane, unless we're looking way up or way down, in which case then the horizon line can be above or below the picture plane. When you're setting up your drawing, I would suggest that you have either a big board, or you can put your paper on the ground and then actually just draw your horizon line, even if it's above or below the picture plane. For us today, we're going to put that horizon line right in the center-ish of our paper, like so. And we'll just label that horizon line. Next, in one-point perspective, we want to think about that imaginary picture plane, and then we want to think about that block, and that one face of the block is parallel to the picture plane, which is giving us converging angles on these other sides. So that would be 1, 2, 3, 4 converging angles. Now, what one point or parallel perspective is capturing is the way that those angles seem to converge at the horizon line at a central vanishing point. Now, on this drawing, we're going to set a scale. And our scale is going to be that 1 inch equals 1 foot. What that's going to capture is, if I was drawing from life, then I could draw this 12 by 12 inch crate in perspective. So, with our little guy here, he is about, and he's going to be a stand-in for me. So this cube, hide these, is going to be a stand-in for this cube. And he is going to be a stand-in for me. So I, right now, am sitting at about, let's try that again. I'm sitting at about 3 feet high. And my cube will make that 6 feet away from me. But first, before we start to get into drawing our cube, we need to find our ground line. So the way that we find the ground line is that we just, however high my station point is up from the ground plane, is, according to our scale, where the ground line would be found. So if I'm 3 feet up and my scale is 1 to 1 inch equals 12 inches, then my ground line would be 3 inches down. Let's change that because that's so tiny. So let's make it 2 inches to 1 foot. 2 inches to 1 foot. And that would put it 6 inches down, which is a little bit more space on our. So that's our ground line. Let's put that in lightly. Ground line. Now we know that at that ground line, that's where our scale holds, and we just changed our scale to 2 inches equals 1 foot. Great. Next, let's find that cone of vision. So if we look over here at our Professor Duke stand-in, then from that station point, which is the eye of the view of the artist, then that cone of vision reaches out from there and is intersecting the picture plane. That circle of intersection is what we're about to capture. Now, the ground line records how high the eye line is. The cone of vision reflects how far the viewer or the artist is from the picture plane. So, if my picture plane is 3 feet away from me, then it would be 6 inches down. Or if it was 6 feet away, then it would be 12 inches down with a 2 to 1 foot scale. So let's imagine that let's split the difference here. Let's imagine that it's 5 foot. So the picture plane is 5 foot away from the artist. And I always like to use string, and I would encourage you guys to use string as well. So if that picture plane is 5 foot away, then 2 to 1, we're going to have a 10-inch cone of vision. If I take my string and a piece of tape, Then I can make a quick compass. Like so. Let's check that again. All right. So that is our cone of vision. Now let's find our mother cube. The mother cube is a cube that's pushed right up against the picture plane, which gives us that's where our scale will hold. So we need to put that cube right on the ground line. And we'll make it a 12-inch cube is going to be 2 inches wide. We're going to start with just that bottom edge of the block right here. And next, we're going to find the converging angles, and we're going to build what we call the ground square. Now we know that those angles seem to converge on one vanishing point, that central vanishing point. So we can just take lines back to the converging vanishing point. Now to draw to scale, we need to be able to find how far back that backside of the cube is. Now if you've got your cone of vision, then you can use a diagonal measure line from either of my 2 front corners to get that backside of the cube. We call these special vanishing points. So special vanishing point right, special vanishing point left. And if I take the diagonal measure line to the special vanishing point from one of the front corners, where it intersects my converging angle is going to give me the back of that cube. So that gives us the ground square. Next, we can use the principle of transparency and draw the rest of our cube, knowing that this plane that front edge is on, as we go up the picture plane, it's still just that same plane, so we can just do 2 inches up, and that's still going to be our 12-inch cube. And we want to try and make that vertical is just vertical in linear perspective until we get to 3-point perspective, in which case then we get convergence on our verticals as well. Okay, let's lighten up our transparency a little bit. And now let's find that top plane. And then we'll use our diagonal measure line. Horizontal is just horizontal. And then we'll just use a little bit of line weight to differentiate our visible edge. And there we have a cube in 1-point perspective. And this cube is, in fact, the mother cube, which means that it's giving us our scale. All right. Now that we've got that 1-point perspective, let's just play around with where that cube could be. So if I've got my picture plane, Well, what happens, I mean, right now it's like directly in front of the viewer. So I'm just seeing two planes of the cube. What happens if I was to shift it off to the left or off to the right, and then suddenly I'm seeing three planes? It starts to look a little bit like a 2-point. However, one plane of the cube is still parallel to the picture plane. So really, it's still going to have a convergence on that central vanishing point. So let's go ahead and push that cube off to the left and see what happens. If it's still on the ground line, then our scale is still going to hold here. And we'll start again by just finding the base. You can still use a diagonal measure line to draw this square to scale. Horizontal is horizontal. There's our base square. Vertical is vertical. Vertical is vertical. Horizontal is horizontal. Convergent angles. The principle of convergent angles is that all parallel angles will converge to the same vanishing point. Diagonal measure line. Vertical is vertical. Horizontal is horizontal. And then I'll use line weight to differentiate that visible edge. Great, so we've seen how we can move horizontally. So what about vertically? What happens then? So let's just pull this cube up. Let's use some line extension. Vertical is just vertical. And let's look what happens to that plane as we approach the horizon line. So let's put a cube pretty close to it. Let's keep our scale. Let's get our converging sides. Can still use that diagonal measure line. Vertical is vertical. And what we'll see is that as we've approached the horizon line, then we see a lot less of that top plane until we are at the horizon line, in which case it's just a horizontal line. As we move above the horizon line, then we'll begin to see the bottom plane of it. So let's put a cube up here. Use the diagonal measure line. Horizontal is just horizontal. We're still on that picture plane, so our scale still holds. Vertical is vertical. Should we use transparency? Horizontal is horizontal. And then we'll use some line weight. All right, that's 1-point perspective. Next, we're going to jump to 2-point. All right, so let's start on 2-point perspective. So with our 1-point perspective, we set the scale. Now, scale in linear perspective is more important for people like draftsmen who are drawing architectural renderings. For our purposes in this class, I mean things like these, right? We've got a plan view mapping out each room. But for us, I want you to know how to establish scale. But for our purposes in drawing an imaginary space, it's not necessary to actually set that scale. So we can set that aside for now while we dive into our 2-point perspective. So let's just start and let's put our horizon line back in. And let's ask ourselves, what's the difference between 1-point and 2-point perspective? So if we've got our picture plane, and then we've got our block in 1-point perspective, what that means is that block has one side of a cube or cube-like form, which is parallel to the picture plane. In 2-point perspective, then it just means that that cube has shifted, and now its sides are oblique to the picture plane. So 2-point perspective is a cube or cube-like form that is oblique to the picture plane. Now our converging angles have shifted from, in 1-point perspective, you just have 4 converging angles. In 2-point perspective, then now you've got 8 converging angles. So the converging angles are this side and this side. So let's get to it. Since we're not doing scale, we can just begin. Let's put in our central vanishing point anyway, central vanishing point. And let's begin with that front edge. Now, if I'm drawing from life and I'm looking for an angle, then I want to use 2 straight objects. Find vertical, in this case, vertical just remains vertical. I find that angle, and then I be very careful not to shift it around, and then I can come over and I can check that angle on my drawing, right? So checking that in life, find the angle, and then I can check it in the drawing. If I'm using linear perspective to just invent a drawing, I can put that angle wherever I want. Now, let's put that angle in. Once I put that angle in, then the rule of convergence starts to come into play, and all angles that are parallel will converge at the same point. So if we're drawing a cube, Maybe I should get that base square first before we build up. Let's do that. If I'm drawing a cube, then this angle meets the horizon line. That's going to be our vanishing point, right? And let's find vanishing point left. And let's build our base square. So, ignoring that height, there's our base square. In two-point perspective, vertical is still just vertical. Use a little line extension here. Vertical is vertical. And what we want to do is just make sure that our all parallel angles are vanishing to the appropriate vanishing point. Okay, then I can use line weight to highlight my visible edges. Knock down. And there we have a cube in two-point perspective. Let's use this same cube to start to talk about diminution in space, or cube multiplication. So the question that we're asking ourselves is, we have our cube in two-point perspective. What happens if I've got two cubes of the same size, one stacked right next to the other? We're going to use what is often called the fence post method to help us to find that cube that's stacked right next to that first one. Really, what we're going to find is any interval. So when they call it the fence post method, it really could be just like, an interval of fence posts moving back in space toward the horizon line. All right. For the fence post method, what we want to do is we want to take our first interval and then we divide it in half, like so. And then we'll put in a construction line from that halfway mark, just lightly driving it back to the vanishing point. Then we'll take a construction line that goes from the top or bottom corner of our interval through the construction line that is bisecting our interval. And then when it hits our converging angle, is going to give us the next interval in our series. So you'll need that first interval to do that. So we go from that front corner through the halfway point on our second interval, where it hits the converging angle. That gives us our next interval. In this case, vertical is just vertical. And then, once we have that, we can build out the rest of our cube. So, let's just do that real quick. Yeah. So there we have cube multiplication using the fence post method. And you can just continue that as far back as you need. Vertical is just vertical. And then the logic of converging angles allows me to build out the rest of that cube. All right, so that's that principle of diminution, or cube multiplication. Next, let's ask ourselves, what happens if we have our cubes and I was to stack one of those cubes right on top of the other? However, they're not stacked directly, but actually one is rotating on its axis. Then we can see that we're not going to get the same vanishing points because the angles have changed. So we're thinking about taking that cube and asking ourselves, how is it rotated on its central axis? Well, what that shows us is that we don't have to always, in two-point perspective, have the same vanishing points. And really, you can have as many vanishing points on the horizon line as you need. So if I was to shift, let's reflect back on, if I'm drawing from life, then I can check that angle. I can find where it vanishes on the horizon line. Then I can use the logic of convergence to build out the rest of my cube. If I'm making it up, I can choose a vanishing point and I can build a cube that way. Right? So if I wanted to turn a cube ever so slightly in this case, the line weight. Let's knock down. So a cube that's subtly shifted. Let's do another one that's a little more aggressively shifted. That vanishing point's going way down that horizon line. And that's an important thing to recognize, that not all of my vanishing points are going to be comfortably on a horizon line that's like on my page primarily. So it's like, recognize that. So it's like, as these angles move out there, then I want them to feel as if they're going to be shooting toward that vanishing point. What I would encourage us to do with our assignments is go ahead and get a string, put your drawing board on the ground or on a wall where you can actually get that horizon line drawn all the way out, and you could go put that string over on that vanishing point, and then you can check your angles really quickly. Just to show you how that works is here. Then I can use that string to very quickly map out my other converging angles. This one, I would need to put it on the ground, stick that on the vanishing point, and then I could do the same thing. All right. So we've done special vanishing points, rotating on an axis. Next, let's do incline plane. Now, for an inclined plane, let's take a look at our cube in two-point perspective. What happens if this cube wasn't a cube at all, but rather a box, and it had a flap that was sitting up and open? Let's take a look. First, let's move a cube over so that we can do that. Let's put it over here. And let's give ourselves, let's give ourselves a vanishing point that is visible. Vertical should be vertical. All parallel angles converge. Let's make this wider. Vertical is vertical. Erase out some of our construction lines. Now, when we get that angle, what we want to recognize is that the logic of convergence still applies. It just starts to apply in a slightly different way. But what we'll see is that we'll take a vertical trace and we'll find what's called an auxiliary vanishing point that will give us the angle in linear perspective. So if that flap was to originate on this angle, then we'll take that auxiliary vanishing point through the convergent vanishing point of those parallel sides. And so let's just take a vertical trace. And then we'll decide if that box flap is coming down. We'd find our auxiliary vanishing point here. Let's take it all the way. And then this outside edge of our box flap is parallel this edge, so it's going to vanish back at the horizon line. And then let's use a little bit of line weight to clarify. Since we're drawing a box, we might put in that inside edge. And let's do another one on the other side. Again, that outside edge is parallel or convergent sides, so it's going to go to the horizon line. And there we've got some box flaps or inclined planes. So we just did 2-point perspective, we covered diminution or cube multiplication using the fence post method, and inclined planes using box flaps. Let's do one more inclined plane that's a little more aggressive, just for clarity's sake. So let's say that there's a plank that's coming off that edge, just so we can see it a little bit more clearly. And maybe we'll push this one more, or keep pushing this, to start to demonstrate a little bit about what that invention of space is all about. So suddenly we start to have, a little bit of overlap here, but we start to get a sense of, space in the scene. Where's that space coming from? Well, our 5 spatial indicators are overlap, that's at play here. Relationship to the horizon line, as these things move back in space, or, as they move up toward the picture plane, often they tend to feel like they're moving back in space. Certainly we have linear perspective, which is converging angles, and the way that that's creating a sense of space. We're using a little bit of atmospheric perspective just in the difference of line weight. And then our last one is scale. So we don't really have scale. Well, we do with our diminishing in space, smaller objects compared to larger objects. So we've got all 5. Okay, let's move to 3-point perspective. Okay. Next we're going to draw an ellipse using the 8-point tangent system. Now, when we think about an ellipse, basically we're just thinking about a circle seen in perspective. So these end up being like a pretty tricky thing to draw intuitively, and you'll see beginning drawers will often get those ellipses a little bit off, so that then you get a sense that whatever that object is that has an ellipse isn't sitting flat on the ground plane. We're going to go over the principles of the 8-point tangent system and how to draw an ellipse using linear perspective. But I think that once you see this, then it's going to help you even just when you're drawing ellipses from observation. So first, let's just start with our same horizon line we've been using. And then we're going to start with a ground square, which we'll use to place the ellipse. Let's start off with a central vanishing point. And horizontal is horizontal. We're going to do it in 1 point perspective. But what we'll see is that once we know the 8-point tangent system, really you can put an ellipse anywhere you've got a plane in perspective. We'll pretend that we're using a diagonal measure line. Horizontal is horizontal. Okay. First, what we'll do is we'll find the center of our ground square. And to find the center of any square or any rectangle, you can just do 2 diagonal lines corner to corner. That gives us the center. Then I can use my converging angles and the central vanishing point to find the center of my two horizontals, and then I can use a horizontal trace from the center to find the center of my converging angles. So these are our first 4 points out of my 8. Next, we're going to take each of the quadrants and divide that diagonal line into thirds. And we're just going to be estimating that because we recognize that we've got a foreshortened situation here. So I'm looking to divide it up into equal thirds. Then to find my second 4 points, I'm going to go just inside that first third on each quadrant diagonal. So that gives us our 8 points. Now, like just a dot to dot, we can connect up our points. To get our ellipse in linear perspective using the 8-point tangent system. All right, let's stick one of these on one of our other cubes just to see how we can place that anywhere. And let's grab our 2-point perspective drawing to do that. So we'll just very quickly use that 8-point tangent system to stick an ellipse on one of our cubes. So we start with corner to corner, corner to corner. That gives us the center of that plane. And then we're going to make sure we're going to the correct vanishing point. It's this one, special vanishing point. And then we'll take our center of the plane and our vanishing point to find our first 4. Vertical is just vertical. Next, we'll take our quadrants and we'll divide it up into equal thirds. And then we'll go just outside or just inside that first third on each quadrant. Then we've got our 8 points. And again, we just link them up like a dot to dot. And maybe we'll just darken that up a little bit. So there it is. Stick an ellipse. Anywhere we have a plane, we can stick an ellipse on it. Okay. Next, we're going to look at stairs. And we'll just use a 2-point perspective cube to get started. All right, before we get started, let's think about, for a section view of stairs is going to look like this. And as we're placing that into a linear perspective system, what we're going to do is we're going to think about each of the inside corners as all connected up on one plane. Right? Now that plane is going to be an incline plane, and we already looked at inclined planes when we were doing box flaps earlier. So you can see that if we can first place the inclined plane, then we know that each of those inside corners of each step are going to sit on that plane. So then we could find another plane representing the outside corner of each of those steps. And we can just use the intersections of the verticals and the horizontals to build out the steps between that slab of 2 inclined planes. So that's where we're going. Let's take a look. And let's mark out our... So first we're going to start with that ground square in 2-point perspective. Do this kind of light. All right, so we're going to start a staircase that's moving up to the right. So first we're going to find our first inside plane. So we'll take a vertical trace through our vanishing point right. And while we're doing this, I'm going to use a string on this one. Again, I encourage you to use strings for vanishing points that are distant or that are just further away than your ruler. All right. Move some of this other stuff out of the way. All right, so there we have our first inclined plane, which is going to be the inside of each of our steps. So now if we just take the height of our step, we're going to just make vertical is just vertical. Vertical is vertical. Is that one vertical? So we just did the height. That gives us the front plane of our first step. Now we can find that second inclined plane off the outside corner. We want to make sure that it's heading to the same vanishing point. Here we go. Great. Now we've got our inside corner plane, our outside corner plane. We've got our first step. Now when we start to go and build each step in between our two inclined planes, we just want to use the logic of parallels and convergence. So every line that is parallel, we know will converge to the same vanishing point. So this first step is going to be parallel our ground square, which means it needs to vanish to that vanishing point right. Each of the fronts, inside and outside of our steps, are parallel toward vanishing point left. So once we've got our inclines, now we just build our steps using our horizon line vanishing points. So I just go from corner, and where that line crosses my other incline gives me that inside edge. Same thing here, inside edge. And then that inside step I think one of my lines isn't perfectly vertical. Vertical wants to be vertical. Ah, seems vertical. So there we have the process for building steps. Do we have any questions? Oh, what's that? Jackson Pollock, do you have a question? Oh yeah, certainly we could turn that staircase and take it up the other direction. Thanks for the question. So if we wanted to do that, let's first just like block out some of the base of this staircase. Maybe it's a staircase, concrete block staircase. And let's put a little bit of a landing on it. Then we'll turn that staircase going up and we'll pull it up above the horizon line so we can start to see how, as we approach the horizon line, then we see less and less of that top plane. So we're going to extend out and make a landing. Like so. Now what we'll do is we'll repeat finding the procedure that we started with, which is we're going to find those two inclined planes. However, we're going to need to do it on a vertical trace out of our vanishing point left because we're shifting where that incline is coming from parallel to the right to parallel to the left. So let's take a vertical trace. And I'm going to use my string again. One little trick for getting the same rise is if I have my vanishing point on my auxiliary vanishing point right, I can just do another vanishing point on vanishing point left at the same height, and it will have the same incline. So now we can just take that angle. Actually, I think I'm close enough to use my stick. This is going to be our inside corners of each step. Then we can double that height. Find that front plane of the first step. Vertical needs to stay vertical. If you don't get those verticals true vertical, then you'll run into slight misalignments. Then we find our second outside edge incline. So there we have it. And now it's just that game of connecting up using our vanishing points, the inside and outside edges of the steps. So now I'm inside to inside. Vertical is vertical. Switch to a slightly darker pencil. So as you can already see, as we're approaching the horizon line, we're just seeing less and less of that top plane. And then as we go over the horizon line, then we're just going to be seeing that underside plane. So let's keep going. So let's do it over here. Under the horizon line, we're getting that situation. Above the horizon line, then we're getting that situation, right? Seeing the bottom side, seeing the top side. If we were seeing it as ellipse, as that ellipse is approaching the horizon line, then until we just get that straight flat line, then it's going to reverse and we'll slowly see more and more. What if we fill this out a little bit and start to build it into, I don't know, maybe a apartment building? Maybe we should talk about three-point perspective before we do that. So, staircases. Let's move to three-point perspective. Okay. Now let's talk about three-point perspective. To begin with, let's do a quick review of 1 point and 2 point. So in a 1 point perspective drawing, then we know that one plane of a cube or cube-like form is parallel the picture plane, like so. Right? In 2 point, then we have no planes of a cube or cube-like form parallel the picture plane, but rather those planes are oblique to the picture plane. So 1 point parallel perspective, 2 point oblique perspective. In 3 point perspective, then even our verticals are no longer vertical, but rather those vertical lines or vertical edges are also going to be converging, right? Now this happens when we have a block like in this configuration, right? But it also happens if I'm looking, or the picture plane is tilted up to look up at, say, buildings, or down, from a bird's eye view, right? So they'll call this like the worm's eye view, tall buildings, the bird's eye view seen from above, or an airplane. Okay. So we'll start with what? Bird's eye view. Seen from above. Now, if I've got my picture plane and I'm going for a bird's eye view, then typically we're going to move that horizon line way up, because as I move up, then the horizon line stays with my eye level. So we might stick that horizon line well at the top of the page, or even outside of that page. Now, when we are going for a 3-point perspective, we're going to get the convergence of what was previously just true vertical out of the central vanishing point. In a bird's eye view, that auxiliary vanishing point, call it vanishing point 3, is going to be found out of a vertical trace through the central vanishing point, and typically well below. So if we use that, we can start to build, some buildings out of that. And then this is our horizon line. So if we were going to do a 2-point perspective, on this building, put the bottom of the building down here. Maybe there's another building next to it, maybe shorter. Those verticals are now converging at vanishing point 3. Maybe there's a street. Everything else is the logic of parallels and convergence. Let's continue our road. Maybe this one gets a sidewalk, put another building, maybe a taller building. So hopefully you can see that. Make it a little darker. Right, for our bird's eye view. Then our worm's eye view is going to reverse all of that. So if I've got my picture plane, I'm going to want to put my horizon line down, maybe even below my picture plane. Central vanishing point. And then we're going to have a vertical trace. Here, we moved that vanishing point 3, that auxiliary vanishing point, down the vertical trace through the central vanishing point. Here, we're going to move it up. You can use a string. Then we could start to build those buildings. Let's make a straight horizon line. Say we wanted to put some windows on this building, we would just So I think we get it. Now, one thing that you'll notice as you do these is as your vanishing points, if your vanishing points are closer together, then you're going to get more distortion. If they're further apart, then it's going to feel a little more naturalistic, a little less distorted. The larger principle is if you've got your cone of vision, then you would want your vanishing point 3 to be at least as far from that horizon line as your vanishing point left and vanishing point right, your special vanishing points from your cone of vision are placed. Okay, so that's a little overview of the 3-point perspective. Maybe let's do a slightly larger drawing with 3-point perspective. Okay, and let's get started. So let's look down on this street scene. So let's put our horizon line up here. Horizon line. We'll put our central vanishing point here, and let's extend that out. vertical trace in search of vanishing point 3. We're going to use the string for that. Start to build some kind of a corner or something. Put a vanishing point left. Vanishing point right. Let's find the bottom of our building. Stick a sidewalk. Maybe there's an alleyway there. And we'll find another building next to it. Maybe a taller building. Maybe this building has a something on the roof. Maybe even has an inclined plane. All right. So I think that gives us the idea, and we can start to see how you can just start to build out this imaginary scene using that three-point perspective, using the logic of converging angles. One thing that I think I want to add on to this is like thinking about developing these drawings using some of the other principles, like we talked about the 5 spatial indicators, which are linear perspective, atmospheric perspective, so using line weight, relationship to the horizon line, so typically as things move up the page, then they're moving back in space, scale, and overlap. So make sure you're thinking about, those kinds of things, and then really play with it. Another thing I want to add is the logic of value. So, we want to think about those 6 parts of value, that direction of light, our first division between light side and shade side. Then we want to divide into 2 values in the light and 2 values in the dark. With the cast shadow to give us our highlight, light, a transition, a core shadow, reflected light, and a cast shadow. So we want to think about applying that, to our linear perspective, right? So if we've got our light coming from this direction, this is going to be that lightest light. This is going to be some kind of a half light. This might be our shadow side. Maybe we'll find a core shadow up here near the top with a little bit of reflected light bouncing in. And then we might think about our cast shadows. We also want to think about local values. So if their asphalt or road has a local value, and then we're going to see that value with the cast shadow on it. Do it with this one. So there it is. Have fun, develop it with value, be creative, use your logic of perspective. What we've covered here in this video is linear perspective in 1 point, 2 point. We did incline plane, we did stairs, we did ellipse, we did diminution, we did 3 point. So I want to thank you for your time, and I look forward to our next video from Fourth Culture Studios, where we recognize that there's culture, there's counterculture, there's the reactionaries, and then there's us. We're doing something different. All right, thank you.